All right, welcome again. The experiment for this week is influence of intermolecular forces on physical properties of substances you'll be working with. I think it's three substances. But first of all, what is intermolecular forces? Intermolecular forces is these are forces between uh, molecules. In particular, when you say molecule, molecules come from the word or from two non-metals. So basically, this is force of attraction uh, between molecules. And there are four types of intermolecular forces you should be aware of. You should learn, commit to your memory. These are the dipole. These are the types of intermolecular forces, types of intermolecular forces. One, dipole, dipole. There is London, say London dispersion force of attraction. There is the ion dipole force of attraction, ion dipole force of attraction, and lastly here the hydrogen bonding. If you look at these types of forces, you should know what they constitute. All molecules they do have electrons, and the distribution of electron in a molecule sometimes is not even. You may find that in a molecule for those with polar or those which are polar, electron at some point can be in one portion of the molecule. For example, hydrofluoric acid, hydrogen fluoride. On the periodic table, hydrogen is less electronegative, or in other words, fluorine is more electronegative compared to hydrogen. An electron tend to be pulled towards fluorine. We say that this is partially positive, and this is partially negative. If this is one molecule, and we have another molecule here with fluorine and hydrogen, there is the force of attraction between these two molecules. We call this dipole force of attraction. For London dispersion forces, this is basically present in all molecules. For non-polar molecules such as bromine, maybe for example this Pr2, the electrons are shared equally. All right, electrons are shared equally, and at some point, because electrons are moving around the nucleus, at some point there is delocalization of electron in such a way that electron might be pulled toward one side of the molecule temporarily. All right, and that will create an induced dipole. And if we have another molecule next to it, if this is partially positive, this is partially negative, this is partially positive, this is partially negative. This type of interaction here we call this London dispersion forces. London dispersion forces. So this is practically present in all molecules, whereas this one is present in polar molecule. How do you know that a molecule is polar? How do you know that a molecule is polar? It's by understanding electronegativity. Remember, electronegativity is the ability of an electron to pull, ability of an atom to pull electron toward itself polar or in a covalent bond. The trend on electronegativity is this. All right. It increase. Let me see electronegativity. It increase from left to right and decrease going down a periodic table. It decrease down the periodic table. So if I know that this element fluorine is on that side of the periodic table, it's more electronegative than hydrogen. We say that the molecule is polar, and if I have a neighboring molecule here, we say that is dipole-dipole force of interaction. Whereas this one, it exists in all atoms, all right, due to the delocalization of electrons. I think it's an example. For ion dipole here, if you dissolve an ionic compound, all right, then we erase this gets on face for ion dipole, all right, from the word ion, all right, ion dipole, like that, ion dipole, force of attraction. You know what ion is? Ion is a charged particle, all right? It can either be cation, it can either be anion. For example, dissolving sodium chloride in H2O, this will dissociate or ionize to produce sodium cation and chloride. All right, this is cation, positively charged, and this is anion, negatively charged. Anion, negatively charged. Now, for ion dipole, for this type of attraction right here, you know what a molecule, all right? This is the molecular geometry for H2O, all right? For H2O, this is molecular geometry for H2O, pan-shape or V-shape, and you know electrons are pulled towards oxygen, which is more electronegative. Compared to hydrogen, less electronegative. We get this as partially positive, partially negative, partially positive. There is this arrangement. Now, if you dissolve sodium chloride, if I have sodium chloride on this side, Na positive, I'll have oxygen, all right? These are oxygen surrounding the sodium ion. So if I have H2O, these are hydrogens, hydrogen. These surrounding, if you look at this force of attraction here, we judge force of attraction right here between oxygen and sodium cation, we call this ion dipole, all right? Ion dipole force of attraction. There is the ion, all right, and then there is the polar molecule. This type of attraction is ion dipole. And then lastly is the hydrogen bonding, all right? Hydrogen bonding, from the word hydrogen, the hydrogen must be associated or bonded to a more electronegative element on the periodic table. This type right here, hydrogen, all right? This is how I look at the hydrogen bonding. There must be hydrogen in it, all right? There must be hydrogen in it. Let's say hydrogen bonded to Fon, F-O-N. I say always Fon for fluorine, oxygen, and nitrogen. This is for fluorine, oxygen, and nitrogen. These are the only element on the periodic table. Which, when hydrogen interact with fluorine, interact with oxygen, interact with nitrogen, you say that nitrogen bonding is in there. Other than that, if there is none of these elements are involved, then we say that that is not that is not hydrogen bonding. For example, methane, this will not exhibit hydrogen bonding. No hydrogen bonding in this because it's none of these elements included in that. So I can say in H2 there is hydrogen bonding. All right, there is hydrogen bonding in H2. If I have water molecule, if this is one water molecule, partially positive, partially negative, partially positive, I can have another water molecule on this side, and the force of attraction right here is hydrogen bonding. This is where we have hydrogen bonding because it is associated with oxygen. You see there is oxygen in there. You should be able to read and see what constitute hydrogen bonding, know what they are. So the objective of this lab is to predict which type of intermolecular forces are present by looking at, all right, by looking at the molecular structure of the compounds you will be working with, all right, and identify whether it is hydrogen bonding or dipole. And remember, this is present in all substances. Now, the strongest among all is hydrogen bonding. Maybe in your lecture, you may be required to list according to increase in their strength, So what are you going to need for today? What you will need is, look at the lab kit. You're gonna need a pair of scissors for cutting the paper. You will need cargoes, of course. All right, you're gonna need the cargoes. And if you don't have a rubber band, that's fine. Okay, you may use a tape. I think it listed that you should have a Scott tape. So what are you going to do? And a thermometer, of course. You should have a thermometer to measure the temperature of the rate of evaporation Let's see. What are you going to do with the three substances you have? What you need to do is cut square. I'm just gonna cut. Doesn't have to be exact. So this is what you need. All right. So this is what you need, a square, and you may want to wrap it around or fold it. All right, I can fold it this way and insert it this way and roll this way around based on what you have. Roll it, and you may use a rubber band to hold this paper around. But if you don't have, you can use a Scott tape, so long as it's able to absorb the water. Let's see, water or propanol. So I'm just gonna have this like this, and if you look at it, this is how it look like. Shouldn't be falling off. You see, shouldn't be falling off. Didn't hold it right, but if you have a rubber band, it should hold it tight. The direction called for, if you look at the paper right here, let me show you where it is. Right here, this is the what you see there is the thermometer tape on the edge of your table. So what needs to be done is immerse this in your substance. Could be propanol. I think propanol, and is it propanol or acetone? You will need isopropyl. All right, and isopropyl acetone, that is nail polish remover. And what you will have to do is record the time it takes for the temperature to cool on the rate of evaporation before I come back to part 1 table 1. How you will fill in this is you read the direction on how to fill in the table right here. That time in minutes it detects for the evaporation. You're gonna record the temperature it detects for every. All right. Look at the procedure. All right. Procedure is for part 2. You should be able to carefully, all right, carefully record the temperature after every 30 seconds. After every 30 seconds, you'll record. So I'm just going to immerse this in the solution isopropyl nail acetone in such a way that you're going to record the temperature after every 30 seconds. After every 30 seconds. From the results, you'll draw the graph and please follow the procedure on how to draw the graph. What I want on the graph is this. You see, what I want on the graph is the how to draw the right graph is you're gonna have a graph of what? You're gonna have a graph of temperature versus time. So you're gonna have a temperature versus time. On this x-axis, you're gonna have temperature versus time. All right, here, and please draw the scale. So here is the temperature in degrees Celsius. Look at my scale, and this is time in. You may want to say second. Is it seconds or minutes? Let's see. I'm gonna be recording the temperature in minutes, not second. This is in minutes. Please draw to scale. Draw to scale, and this is a plot of what? Temperature. This is a plot of temperature versus time. Time in minutes. For acetone, you're gonna do for isopropyl and the other substance. And probably it's gonna look like this. All right, it's gonna maybe look like that. This will be your maximum temperature, and this is your minimum. Please indicate the minimum and the maximum temperature, minimum and maximum temperature. You'll identify the, of course, you're gonna do the part 2, that is determination of the rate of evaporation, how to serve extension for H2O, isopropyl, and acetone. Basically, you need the droppers. You're gonna need the penny and the dropper should have come with your lab kit. The dropper should have come with the lab kit. Other than that, the rest of the information pretty straightforward. If you have any question, you can send me an email and I'll be able to help you. Other than that, I'll see you tomorrow. Thank you.